Hello to all my students. Now I'm going to explain the logic gates, which is a very important part of electronics. Now see which of the different available gates are NOT, AND, NAND, OR, NOR, XOR and XNOR. Out of these, the fundamental gates are OR, AND NOT. Now if you look at the algebraic expression, then you can understand that NOT means if A is the input, then NOT is just the reverse of that. The symbol is like this. If X is the output, then X will be equal to A inverse. That means if the input is 0, the output will be 1. If the input is 1, the output will be 0. Now see the AND gate. The symbol looks like this. It's just like the shape of D. A and B are two inputs. That means in NOT gate, there will be a single input. But in all the other gates, there can be more than two inputs. And here I am showing with only two inputs. Now see if A and B are the inputs and X is the output. This AND gate performs logical multiplication. So if the two inputs, these are the different combinations possible since this is a part of digital circuit. So what are the combinations possible for 2 bits? 0 and 1 are the 2 bits. So number of combinations possible are 2 to the power 2, that is 4. That means 0, 0, 0, 1, 1, 0 and 1, 1. Now if both the inputs are 0, then for logical multiplication the output will be 0. If both the inputs are 1, the output will be 1. If any of the input is 0, then the output will be 0. That means the output will be 1 only when both the inputs are 1 in this case. Okay, now see this NAND gate. This is just the reverse of AND. So AB complement. So you can see that this is just like the shape of a D with just a bubble at the end. So this indicates the inverse of AND. So if you look at the truth table, you can see that again we are taking the 4 combinations and here it is 1 for all the 3 states. Only when the 2 inputs are 1, the output will be 0. Just the reverse of this AND gate. Now see the OR gate. This is the symbol of OR gate. This performs logical addition. Here also these are the 4 inputs. And if you see the output, since it's performing logical addition, so only when the 2 inputs are 0, both the inputs are 0, the output will be 0. For all the other 3 cases, the output is 1. Now NOR gate performs just the reverse of OR. That means A plus B bar, just the complement of OR. So it's just the, so if you look at the symbol, it is just as the shape of OR gate with a bubble at the end. So if you look at the output will be 1 only when both the inputs are 0 and in all the other cases the output will be 0. Now the XOR gate, you can see it just resembles the OR gate just with another curved line like this at the input. And the symbol is like this with a plus within a circle. This represents A XOR B. So here you can see that the output will be 0 when both the inputs are equal. That means when both the inputs are 0 or both the inputs are 1, the output will be 0. And in all the other 2 cases, when the inputs are different, the output will be 1. And see the XNOR is again the reverse of XOR. So if you look at the symbol, it just represents the XOR gate with a bubble at the output. So this bubble represents the complement. So the algebraic expression will be A XOR B with a bar at the top. So the output will be 1 only when both the inputs are equal. When both the inputs are 0 or both the inputs are 1, the output will be 1. When the 2 inputs are different, then the output will be 0. So I think you have got a basic idea about the logic gates. And in the next step, we are going to analyze the different types of logic gates with different mathematical expressions and how to do the simplifications and all. Thank you. Hello everybody. Now I'm going to discuss about operational amplifier, which is in short called op-amp. Now, if you look at this symbol, this is a symbol of op-amp. It's just triangular in shape. It has 2 input terminals. One is the plus, another is the minus. The plus terminal is called the non-inverting terminal and minus terminal is called the inverting terminal. That means if you apply any signal to this plus terminal, the output will be in phase with the input. And if you apply any signal to the inverting terminal, the output will be at 180-degree phase difference with the input. So it's called inverting input terminal. Now the op-amp always operates with two supply voltages. One is the positive supply voltage, another is the negative supply voltage, and there is a single output. This op-amp is also called a differential amplifier. It's an amplifier because the output will always be the amplification of the inputs, but the difference of the two inputs will be amplified at the output. And if any common mode signal comes here, that means suppose noise comes here, then that will be rejected at the output. So op-amp is basically a differential amplifier. If you see another picture here, it is shown. This is the pin diagram. Actually, op-amp is 741 IC. The IC number is 741. IC means integrated circuit. Integrated circuit means a number of components are integrated on a single silicon wafer. Generally, we take the semiconductor wafer as silicon. So this is the chip number is 741, and these are the pins present in the IC. This is an 8-pin IC. Op-amp IC 741 is 8-pin IC, and all the 8 pins are shown here. So if you see this inverting terminal minus, it's the pin number 2. The non-inverting terminal plus is the pin number 3. The output is pin number 6. The positive supply voltage V plus is the pin number 7, and the negative voltage V minus is pin number 4. And you see there are some other pins like pin number 8 which is not used. Pin number 1 and 5, both the pins are written as offset null. Actually, offset null adjustment is made between these two pins. It can be done manually, but nowadays in the ICs that are available already this offset null adjustment is being done. And this is the IC shown here, an IC, the integrated circuit of the chip that looks like this. And this is the symbol of op-amp. It's triangular in shape, and triangular shape, this actually indicates that it's an amplifier. Thank you.